Hello. Hi. How was your weekend? Hope everyone had a great weekend. Okay, so we are already almost the end of November. So yeah, I know things are, you have a lot of things to do and the contents are getting more hard. So yeah, let's do this until the end of semester. Let's try to finish this. And yeah, we have a lot of things to do. But yeah, I have announcement today. So the project midterm report is graded and available on ETL. So you can check your score. And I also gave very detailed feedback for each team. But because of the ETL's functionality, those feedback and the score will be shown only to the students who have submitted. Actually, one team submitted by two students, so I released the score for both of them. But anyway, if you didn't submit by yourself, you will not be able to see the comments. So please ask your colleague or leader who actually submitted the reports, and they will be able to share the score and the feedback. So I hope most of you already have done. For those who don't know this, you can check the score and feedback on ETL. And I also released the grading criteria for this midterm reports. So as I mentioned, I expected you have finished like 70% of the final report by the midterm report. So I graded up to like 130 points at most. And if your report got like more than 100, then you got the full marks, which is 100. And the final paper submission is open, so you can always submit. And I have all the details of the submission instructions. You have to submit basically the CBPR format paper of your project reports and more things, which is one-page summary of each member's contribution and the source code for your program or the LaTeX files. So please refer to the descriptions written there, and please do not be late. Again, this time, this will be 10 a.m. instead of 11 a.m. because we need some time for preparation of the presentations on that day. Okay? Any question about this? All right, okay. So let's do some review today. So like last time, I'm going to show some pictures, and you're going to describe what it is and how it works. So let's do this. What is this model? Junho, can you explain what is this model and how it works?
Professor, can you hear me?
Yes.
It is maybe BERT, and it gets a sequence of text, and we embed the text in tokens and add position embeddings, and then we input this token to encoder part of transformer, and then we get output by some task. Yeah, that's all.
So can you explain more about what are those tasks?
Oh, I can't remember exactly, but we can output some. We can output. We can mask some words, and we can get the answer of the mask, and I cannot remember what task was. So sorry.
Okay, that's fine. Let me ask another student. 소연? 박소연?
Yes, Professor.
Yeah. Do you remember what was the another task?
So the task one was masked language modeling, right?
That's what Junho said. And the other task?
And the other task is next sentence prediction.
Mm-hmm.
So just predict the two sentences are consecutive or not.
Yeah, that's great. Yeah, thanks both of you, Junho and Soyeon. So yeah, this is the BERT model, and we have input of tokens, which is a sequence of tokens, word tokens, and we have two sentences actually taken from the corpus, and half of them are selected such that two sentences are actually directly connected in the original corpus, and for the other half, we have just randomly sampled two sentences from the entire corpus. So this SEP separator indicates the end of each sentence. And at the beginning, we have the special token called classification token, or CLS. And we use this token to classify if these two sentences are consecutive or not. And also, as Junho said, we mask some of these words. And for that particular token, we classify what would be the plausible token, which is located there, by using the softmax classification. So that's basically the BERT model. Great job, both of you. So we are going to use this structure for multimodal learning today. So this is really important to know. And we also learned another model, which is called vision transformer. So this is a quite brand new approach, and they use the transformer to learn the image or video understanding. So let me ask to June.
Yes, Professor.
Okay, can you explain how this algorithm works?
So the VIT divides the input image into 16 patches, and it encodes each patch into each representation and feeds the representation and the positional encoding into the same structure like BERT, like transformer. And the encoder predicts which patches should be like positioned. And also we could modify the MLP classification layer to additional usages like representation learning or classification or something else.
Okay, great. Thanks for explanation, June. So yeah, almost correct. I would like to just fix the very beginning. You mentioned that the image is split into 16 tokens, but actually each of those token image patch size is 16 by 16. The number of patches in the image depends on the original size of that. So yeah, but that's just hyperparameter, doesn't matter actually. And this MLP head is designed to classify the entire input image. So yes, we can actually use the embedding here for as a representation learning for this image, of course. But the original design is for classification. Yeah, other than that, it was perfect. Yeah, thanks. So we learned this model, and yeah, I'm not going to ask, but we also learned about its extension to the videos. So yeah, please review the material if you're not familiar with. And yeah, that's the end of today's review. Any question so far? Okay. So in the last lecture, we learned about VBlbert. And today we're going to see VBlbert, which looks very similar. Actually, they stand for the same thing, Visual Language BERT. So they actually developed these models at the same time. So each of those papers probably cite to each other because they knew each other and because they were available on archive or something. So one of them named as VBlbert and the other one named VBlbert, but basically they are the same thing. And they are solving exactly the same problem, but their approach is slightly different. So in the VBlbert, they, so let's go back to the picture of the VBlbert model. So it was like this. You may remember that. So this was the VBlbert model we actually covered in the last lecture. So they basically use the transformer structure, and they have the token embeddings for the word and visual embeddings for the image. And image was split into different region of interests. And they use the contextualization across these two different modes to learn embeddings for each of those tokens, which is word or image parts. So they actually, for them, this is just direct application of the BERT style transformer model. And this transformer itself was just pure transformer, which is different from VBlbert, which we are going to talk today. So this is similar to VBlbert, but added cross-modal attention with the BERT. So what is the cross-modal attention here? So the input is very similar. The input is just the image parts, the part of the images, and the text part is just a sentence describing this figure. And they use the embedding layer as like other natural language models. And then they have just regular transformer to contextualize the words tokens within this sentence. And then also from the visual side, they use some embedding model from some previous, some pre-trained image models. And then they stack these layers, which is the cross-modal attention and regular transformer is repeated. So it's k times of these things. So the TRM, the transformer, is the same as the previous, the transformer in each of these modes, but this co-TRM is different, which is nowhere in this paper. So let's see how it works. This part, as I said, this is exactly the same as the previous regular transformer. So all the query key values are coming from its own mode, which means in the sentence part, the query is one word, and the key and values are also from other tokens, including itself in the sentence. And same for the visual part. So query is one part of the image. Key and values are other parts of the image, including itself. So that's just regular transformer block we have in this part. But this co-attention transformer is like this. Looks complicated, but actually it's not. This part, which is the greenish, this part is the visual part, and this purple color part is this the text part. But then the query is coming from its own mode. So for the visual part, we have the query from the image part, and the for the text part, the query is one word in the sentence. But they refer to the keys and values from the other side, which means you compute the similarity or relevance between the query word and each part within the image. And based on that similarity, you're going to contextualize to the other mode, from text to the visual or from visual to the text. So this is not actually new to us. We actually have seen very similar things in the decoder part of the transformer, right? In the decoder part, do you remember that? We had two layers of the self-attention. And the first part was masked self-attention head, multi-head self-attention, which is getting the text from, getting the output so far and just contextualize within those tokens, right? And the next one was we were taking the queries from the input side, but the keys and values from the output of the encoder part. So if we translate from French to English, for example, we were looking at the French words to generate the next word in English, right? So this is actually very similar to that architecture. So we take the query from each own mode and we refer to the keys and values from the other mode to contextualize to each other. Okay, so this is different from the VBlbert. In VBlbert, they just use this style of the regular transformer, but there the queries and keys and values are all mixed. So they just combine all, just union all the visual tokens and the language tokens together. Then they contextualize to each other just using this regular transformer. Here, they split the two towers, but they just exchange their information using these co-attention transformer layers repeatedly. Other than that, these regular transformer, they still use their own mode, not cross-attention. That is the difference implementation of their ideas. But basically, the bigger picture or the philosophy is very similar. They would like to learn the relationship between the sentence and the image, the visual signals, to contextualize from each other. So the task in the VBlbert were two things, very similar to the BERT, regular BERT. So one is masked multimodal modeling task. So this is similar to the MLM, which is the key task in the BERT, which is the sentence completion. So here, they mask the visual words and the textual words, both of them. And for the language part, this is exactly the same as MLM, just classifying which words should be there from all the corpus. But for the visual side, what do they do? This is same as VBlbert. So in there, they have run the faster RCNN to classify each region of interest and had the pseudo label for each of those parts. They used it as a ground truth of the class for that patch. So actually, they did exactly the same thing. So for these masked image areas, they go through this vision, the cross-modal transformer, and then they have finite number of possible classes in the data set. So they use these faster RCNN results to classify what is the correct class corresponding to this image hidden in this input. So this part is you're already familiar, right? It's just doing the MLM on the text, and very similar ideas applied to the visual side using the faster RCNN labels. For the second task, multimodal alignment task is analogous to NSP, next sentence prediction in BERT. So in there, recall that we had two sentences, and we classified if those two are consecutive or not, or that means actually relevant to each of them or not. Here, we have one image part and one sentence part, and we have the CLS token for summarizing the text part. And this is actually the CLS part for this vision part, but they named it as an IMG, stands for image. So this image token summarizes what's the contents within this image, and the CLS token summarizes the contents in the sentence, and they use these two to classify if they are aligned or not, which means if the sentence is a right description of this image, then they are aligned. And if they are misaligned, which means this text is something random description, which is independent of this image contents, then it's not aligned. So in the training data set, they have a pair of an image and a description. So if they use those pairs as is, then it's aligned. And for these negative examples, they just mix randomly. So for each image, they just randomly choose some other text descriptions from the data set. So that's how they create this data set and train this multimodal alignment task. So using this VBlbert model, they have achieved actually a lot of interesting tasks. So one is the caption-based image retriever. So actually, there are a lot of interesting applications like this. So this is actually the right task that they have actually optimized. So given a text describing an image, their task is retrieve the most relevant images from the corpus, which means similar to search. Actually, you search image search, you search with some text keyword in the search engine, and then it shows the list of images which is relevant to that query. So if the candidate set is really huge, then that will be actually used as a search. So here, we have these texts, and the image can be also split into different patches using the faster RCNN, finding the region of interests. And then, because we already have trained this model, these two tokens, the image token and the class token, will be able to compute their relevance score quite correctly or quite accurately, right? Because they are the classifier was trained to estimate if these two are relevant or not, or aligned or not. So if they are actually aligned, then they will have the high score. And if these are not relevant, then they will have low score. So for given text, we can actually compute these scores for all the images in the data set and then sort by them. Then we can take the top K, which will be the search result, basically. So we can simply implement some very simple search engine using this. Okay, so yeah, they have many other interesting applications in the paper. So please refer to that, which is actually similar to what we've discussed in the VBlbert in the last lecture. Okay, then so far we talked about image models, transformer-based image text models. And now we are going to see transformer-based video text models. So how can we apply the transformers to learn video text correspondence instead of image text correspondence? So recall that transformers take a sequence of tokens as its input. So we were worrying about how can we apply or make the one image as a sequence. But video is actually easier. Video is already sequential. We have a sequence of frames. So it's by nature, it's actually sequential. So we can just give the sequence of frames or frame features to this transformer as an input. Then the bigger problem is this. How can we collect video text pairs? We need the data set to train, which is a positive pair between a video and a text. Or this text means some right description of the contents of the video. So we need some text description. What is this video about? And collecting those kind of data will be really, really costly because we have to ask some people to actually watch the video and then summarize in their own language what's the contents of this video. So that will take like a minute or two or even 5 minutes for each example. So it will be really expensive, as we actually discussed at the beginning of this class. So any other easier way to collect noisy labels, even noisy labels of these positive video and text pairs? Any ideas? You can use the chat if you have any ideas, other than directly asking people to actually rate it. Well, because already I shared this, yeah, YouTube video title. Yeah, thanks, Angon. Yeah, so yeah, you may think of some examples like this. So where if you have a web search engine like Google or Naver, then people actually type some queries and then they click some videos to watch, which means it's a kind of positive signal, right? They wrote something in text, and then as a result, they got some videos and they actually watched it, which means probably means that that was the right video that they were looking for that query. So we can collect the pair of those search query and the clicked videos. Or in YouTube or other video sharing platforms, as Angon said, the video and its title or descriptions, or even the comments in the video. So that can be a weak signal of the positive relationship between the video and the text. And Donghyun said caption of video, yeah, which is here. So in the video, we have actually comprehensive information. Like we have visual signals, audio signals, but also some of those speeches can be transcribed to actual text. So that is called ASR, automatic speech recognition. So ASR, this term will be commonly used in this rest of this course. So please be familiar with this. So yeah, what I say now, and I record this as a video and I upload this to YouTube, then Google actually run this ASR model to transcribe what I say, and that's quite accurate, interestingly. So we can actually use this ASR and the scene where that speech was actually happening, then that can be kind of used as a positive pairs between the visual signals and the speech text. So, or you can users actually can upload the captions. That's what Donghyun said. So either by machine or either by human, either's fine. Just transcription of the spoken language in the video. So yeah, these are the way we can collect these pairs, positive pairs of video and text, or image and text, and we can use that as our data set for this problem. So let's come to the first model. It's called Videobird, not VBlbert or VLBert, but now they have Videobird. So as this name stands for, this is actually the video, not image model. So as I mentioned in the before, the videos are a sequence of frames. So they now have a sequence of frames in some features. They actually use the S3D features. The author of this paper is the author of the S3D. So they use the same features here. And for each training example pairs, they have one video and one text, which is ASR from the part of the video. So for example, here place the steak in the pan. This is the sentence. And this is some part of a video. It's which is, I don't remember how long it was. I think it was taken from the video where this ASR, this sentence is actually spoken. So in that range. So they focused on the cooking and recipe videos because these are the easiest type of videos that we can apply this kind of technology. Because usually when you cook something, it usually follows some recipes step by step. So and also in the cooking videos, they show how you are actually cooking, something like this. And the speaker usually talks about what you have to do in each of those steps. And that is quite well matched to the written recipes. So yeah, this kind of data set is widely used for this kind of transformer models training. So okay, now we have another one more problem, which we didn't have in the image case. In image case, what we did was actually using the faster RCNN model. So we feed the input image to the faster RCNN, and it detects all the potential items discovered in that image, right? And we used all of those region of interests as our sequence input. So what we had was each of those image patches with some items that we might be interested in each of them. And we actually had some pseudo labels by the faster RCNN model to classify what it was, which means we had actually the label for each of those items or the patches. But now the input is a sequence of just frames. Of course, they can still run faster RCNN for all the frames and use all of those as all of those region of interest as sequence, but then it will be too long, unfortunately. So they actually tried something different. Instead of using the faster RCNN to classify each of the image patches, they just used the S3D representation of the entire frame. And we still have the sequence of frames because we have multiple frames in the video. So now we cannot directly use the classification of each frame, right? Recall that in MLM, we mask one word, and then we classify what that word should be among all the possible candidate words in the vocabulary. Even though it's like tens of thousands or hundreds of thousands, but still it was okay. We were able to do that. What about for these frames? Can we classify those frames without any labels? We can't. We mask them and we want to try to figure it out what it is, but then what? We don't know what it is in ground truth because we don't use the faster CNN here. Are you following? Okay. So what we should do here? So their solution was using the clustering. So the frames, the S3D features of each frame are clustered. So similar frames are gathering together, and different frames are far apart, far away from each other. Then use the closest centroid as their representation of each frame. So here are some examples. These are 6 frames in some video, and they clustered all the frames like these in the data set. And then for each of those input frames, they exchanged it to their representative centroid features and visualized what it was. So this frame, for example, is represented as this frame. You see that visually it's very different. I mean, the pixel-wise, they are completely different. But you see that semantically, they are actually very similar. It's just one cake. And for this one, probably this is the next few frames after this. But now its representative looks like this. But still, these are very different. But still, semantically, they are talking about the same thing. And this one, lady is talking about some cake. And actually, this one is the same. So they are showing this because they argue that this video tokenization actually works and does not change the semantics of each frame representations. So they clustered the entire set of frames in the data set, and using those centroids to represent each of these frames. And then now what we can do, we can hide one of these frames, and we can figure out what it should be among all of those centroids, because the number of centroids is some small number, like several hundreds or several thousands, not like all the possible combination of the pixels in the image, right? So that's how they circumvent the problem of this classification. So here's the Videobird model. So when they trained, they actually applied 3 different tasks. The first one is the linguistic visual alignment task. So it's the same as the previous model, the VBlbert. So this class token summarizes all the information in this sentence and also the frame tokens here. And they use some classifier on top of this class token to classify if these two are relevant or not, or aligned or not, so from the data set. Okay? And this MLM, masked language, is same as BERT. Just one word is masked, and then we just classify what that should be. But now the difference is that in the BERT, we had only this text part. So place the something in the pen, and then there can be a lot of things possible, like here steak or chicken or some vegetables, whatever we can do put here. But now in this Videobird model, they actually look at the image signals here from each of these frames. So if these are well embedded and they learn the relationship between these text tokens, then they will be able to figure out, oh, this is steak. So they can actually take advantage of these frame signals as well as the text signals here. And masked frame modeling is what I just told. So same as before, this image, one frame is masked out here, and then it needs to figure out what kind of image should be there. So we see that this is the empty pan, and this is well done steak. So what would be expected in between those two? The start of the grilling, like the raw meats, sounds reasonable. So using these tokens, actually they can, because these images are clustered, and then we use the centroid of each of them. So we can classify what it should be among some finite number of possible clusters or classes. So very similar to MLM, but now they use the cluster centroid instead of the actual label we had in faster CNN case. Okay, so using this model, let's summarize. So the input is a pair of a sentence and a video, which is a sequence of frames. All of these are embedded as a features. Then they contextualize to all other tokens within these two input pair. And then they solve these three tests to figure out if these two are aligned or not, and what is the hidden words or what is the hidden frame should be. So that's what they do. And eventually, they will have better representation of these words and these clusters or the centroids. And they can use these land models to do a lot of interesting things, which I'm going to show here. The first one is the recipe illustration. So what they wanted to do with this model at the beginning was like this. They have some recipe written in text, only purely text. And they wanted to build some models to extract the relevant images for each of those steps to automatically generate the visualization. Because people search recipes a lot on Google or using their AI speaker. And then they wanted to show how it actually works using videos like on YouTube or at least images in the image search. So they built this as kind of proof of concept. So they give, using this trained model, they give the full sentence, place the steak in the pan, and only one image is being used, but that is masked. Then this model is, when we just run the inference, then this model is kind of forced to generate, or not generate, actually select the one of the centroids, which is best mapping with this sentence, the semantics of this sentence. So that's how they created this sequence of images for each of these query texts. So for this one, season the steak with salt and pepper. And this was the centroid image, which is most suitable for this sentence, for example. So that's how they use this model for recipe illustration. And this is future frame prediction. So now they don't have any text. Only one frame is given, which is the empty pan here. And then they are forced to figure out what are these, all the masked sequence of the frames. Then they can find out these four, which is the raw meat and done, well done grill, the steak. And then I don't know what it is. Yeah. Or for this one, they have some ingredients for baking, I guess, and they put it in the oven, and then they are done with these cakes, something like this. So this model kind of learns what it should be after this step, because they have trained on cooking videos or recipe videos, and its text pairs. And yeah, this is also interesting. So the task is the zero-shot action classification. So given just one, or given some video clip, like short clips, and then they wanted to generate some sentence, what it is about, which is really hard task for AI. But they, so that's how they gave some sentence template like this. Now let me show you how to mask the mask. So yeah, here, the how to mask the mask, then this model, if this model is trained well, then it will kind of know that the first mask will be some verb, and the second mask will be some noun, because it's in front of that, it's the. So given this video signal, video hints, and this structure, this model is kind of forced to find the best matched verb for this part and the best noun for this part. So for example, for this one, how to something to something, and then they find like the verb was like make, assemble, or prepare, and the top nouns were like pizza, sauce, or pasta, which is perfect, right? Probably this is something else. I don't know. It's kind of 빈대떡 or some quiche, But anyway, pizza looks reasonable for this one. And for this one, the top verbs was like make, do, or pour, which is great. And the top nouns were like cocktail, drink, or glass, which makes sense. So using this model, they were able to kind of describe what is the video about, or what is the video clip about. And of course, we can do the video captioning in a slightly different way. So just giving the entire video, and then give all the sentences the masks, and then it will be able to describe what is this about using some text words. But yeah, so this is their results. Like the ground truth was for this video was add some chopped basil leaves into it, and their model output like chop the basil and add to the bowl, which is great. And S3D is their baseline. So without these BERT style models, just using the S3D features only, without any contextualization, then cut the tomatoes into this thin slices, which is we don't see any tomatoes here. So I guess these examples are cherry picked by the authors. Usually, most of the examples in the paper are cherry picked, not just regular one. That's all we know. But still, this is amazing. So this model was quite sensational when it was published. Okay, so that was the Videobird. And the next model is CBT, Contrastive Bidirectional Transformer, by the same author of the Videobird. So they actually, it seems like they didn't like the idea of the clustering, because clustering is not end-to-end trainable. You have to, the clustering should be done outside of the model training, because it does not pass the gradients, and yeah, it's not basically just end-to-end trainable. So they wanted to remove that from their model to train the entire model end-to-end, just give the data and we get something, boom. So that's what they wanted. So they their follow-up work is called CBT, and that was published in 2019. So the model looks like this. So the video is given and the ASR is given, the text is given. And then the first part is very similar. They extract the word embedding using the BERT and use SVD to extract the visual features. So each of these frames are now represented as vectors. And then this BERT means this is the text part transformer. And this CBT is the video part transformer, just unimodal transformer. They don't have the cross-modal yet until this part. And then using these representations from each of these transformers, they train another cross-modal transformer. Actually, this was the Videobird. So they used the Videobird to mix these information to have their final results. So interestingly, actually, this part, they don't have any novelty. They just use the Videobird. But their novelty is happening here, the CBT, because in the Videobird, what they did, they clustered all of these, and when they trained this cross-modal transformer, they had to use the centroid ID for each of these frames. But they really wanted to remove that part, and the gradient can flow from all the way from the end to the very beginning of this video model. So the innovation is actually happening here, and that's why they call this paper as CBT, even though this part looks like the most important part. But so here's the model structure of the CBT. Let's see the details. So this part, the text part is the same, right? It's we just have the BERT and word embeddings, and then we solve the MLM and the next sentence prediction. That's it. So let's just see their mathematical formula. So the BERT of the loss function of the BERT looks like this. So this y minus t means this is the masked token. So given t is the masked token, and y minus t means the rest of the tokens except for that masked one. So given that incomplete sentence, they estimate the probability of each word, and they would like to maximize the likelihood of the actual word observed in the data set. So that's how this loss function looks like. They use the maximum likelihood estimator to maximize this probability function, assuming all the words are independent to each other. That's basically this BERT loss function. And then this is the softmax classifier. So given each candidate, they estimate the similarity or relevance score for each of those candidates given this sentence. And then they use this softmax function to classify which word they should be. So that is just BERT model. Now, we have this visual part. So these sampled frames are first encoded by S3D, that's what I said, and then goes through a transformer called CBT. So this is basically a transformer. As image is a real valued vector, not a token, they use contrastive learning. So before, in the Videobird paper, they used centroid ID as their classification target. But now they changed that loss function part to contrastive learning instead of the softmax classification. That is their contribution of this paper. So let's see this loss function. So it resembles the loss function of the BERT, but instead of this maximum likelihood estimation, they actually minimize the NCE, noise contrastive estimator. Remember that? I told you that you're going to encounter that once again, and that's here. So this one looks like this. Actually, this is really interesting because this one resembles to the softmax loss function. Instead of summing over all the candidates in the denominator, they have some negative sets for each t, and they actually sum only those over negative sets, not the entire possible sets. Because it's impossible. You cannot sum over all the possible images in the data set. So this part is the positive, which is the frames from the same video. So from the same video, you have multiple frames, and they are randomly chosen. So if the two frames are belonging to the same video, they are used as a positive. And for these negatives, frames from other videos are just randomly chosen. So in the actually they use the mini batch. So in the mini batch, we suppose you have like 32 videos in the mini batch, then you have the frames from 31 videos. So those are used as negatives here. So let's look at their loss functions in more details. So in the case of BERT, they use softmax. So basically that encourages the model to learn to identify the correct token compared to all vocabularies. That is this part, the denominator. So let's see the notation first. The BERT input, or the actual embedding for the word t, is denoted as ET, and ET hat is the predicted embedding for the word t by your model. And then you're going to maximize this score if this ET is actually the word observed in the data set. So this part is the actual embedding for each of these candidate words, but you'd like to maximize this because for the particular word t that was observed in the data set. Anyway, the most important thing here is that you're going to divide by sum of the scores for all the vocabularies, which is different here in NCE. The main difference is that you have some much smaller number of negatives randomly chosen, actually based on the mini batch, and you compute the negative scores for only those mini batches and just divide it by the positive plus those negatives, and still you can maximize the likelihood of the actual frame ET compared to those negatives. You don't have to actually sum over all of these things in the case of the BERT here. So that's how they apply this NCE into the CBT model. Okay? Okay, so this is the summary of the CBT model. So the input to the model is a sequence of frames, x1 to xm, and the text tokens y1 to yn. And then they train some cross-model transformer to learn the relevance between these x and y. if they are from if actually this y is describing this x, or they are actually aligned in the video, anything, some positive relationship between these two. So yeah, so that's mainly their goal. And let's see, x and y are concatenated and fed into a cross-modal transformer like Videobird, producing output embedding sequences. So this is happening after we have trained each of those subcomponents in each mode, which is the BERT for the text and the Videobird for, the CBT for the visual part. And then they apply this Videobird to learn the actual relationship between these two different modes. And there they also use the NCE loss in a similar way. So eventually, H goes through some shallow MLP to compute correspondence score between these two modes. And the entire model is now trained end-to-end. They don't have to cluster to create those centroids. That part is gone. And weight summing all three losses. So they have three losses. BERT is for the text part. CBT is for the visual part. Cross-modal is for mixing them, fusing them at the end. So they have, for all of these three losses are summed with some weights, and then they can actually train the entire model end-to-end, which is great. Yeah, so because they actually just changed their model inside of the Videobird, their application is actually very similar. So we skip their experiments. And yeah, let's quickly see two other models. Actually, Hammer, this one is what I participated last year at Google. So our target was solving moment localization task in video corpus. So you can think of some search task, like video search task. Given a text query, what is the most relevant video to this query? But before than that, we can actually thinking of simpler problem, which is given just one single video, and find the time window of an event that is described by the given natural language query. So you're given a video, which is like 2 hours long, some movie, just thinking about some movie. And you may remember some scene that you'd like to watch again. And you can search on Google to find that scene with some text query, some text descriptions of that. And then it shows the actual starting point of the video on some YouTube videos or something that you can actually watch that part. So if you're dealing with only one single video, then that is called moment localization in a single video. And MLVC is harder task. You actually have multiple videos, not one. And the task is where is the contents that you are looking for, which is described in a text. And the answer should be, this is the video, and that is happening at this point, like 5 minutes and 30 seconds or something like that. So here, for example, how to butterfly a chicken, you search on YouTube, then we would like to have something like this, not just a sequence of videos shown, but actually you have to watch this part or this part or this part. That is what you'd like to have as an output for this task. So what we should do, we actually want to optimize this. Given the text query, for all the possible moments, we would like to have this probability of this query actually describing this moment. And if the score is high, then we would like to actually show that. But ranking all the possible moments in all the corpus, that's not feasible, right? We have millions or billions of videos, and all the possible moments, even in a single video, is not feasible if the video is quite long. So what should we do? We use the Bayes rule to split this into two problems. So probability of moment given query can be split into this. The probability of video, or particular video, given query. And then given this query and video, probability of moment. And we sum over all the videos as an intermediate variable. Mathematically, these two are exactly the same. I'm not doing any approximation yet. mathematically it's exactly the same. We go over all the possible videos to estimate these probabilities, then it will be exactly the same as what we would like to have here, right? I'm not doing any trick yet, but okay, yeah, before we talk about that, this part is called video retriever. Given the query, we would like to find the video, which is different from the moment. We don't need to think about which part it should be, but we just want to find the video first. So it's called video retriever. So it's lower resolution at the level of video, and it filters video during the inference only that. So this is actually what we currently have at the video search in YouTube or anywhere on or like web search engines. Then we need to solve the other problem, which is called moment localization within a single video. That is actually what I said as a simpler problem in the previous slides. So this is more higher resolution task. So given a video and a query and where it's actually happening, that's this task. But instead of we solve this for the entire videos, we skip all the videos that we didn't retrieve in this lower resolution task. So we just take the top K. The K can be like 10 or 20 or 100, that's it. If we do this for all the entire videos on YouTube, that will be kind of billions of videos, but we can just do this with just 10 or 20. That's much simpler. So this high resolution task is much more expensive, but we deal with only much smaller number of videos, then it will be doable. So this is the approximation actually I applied here. So for each of these tasks, what we've done is the contrastive learning for this video retriever task. So in the training data set, we have a pair, the positive pair of text and the clip. So if these two are aligned in the training data set, so this is actually the positive signal, the positive pair, and then we randomly change either text or the image to something else. So query minus is one more negative we created by just randomly substituting the text part. And video minus is another negative that we created, which we randomly changed the visual part of this. So we have total 3 pairs, the positive pair and 2 negative pairs. And using these 3, we just compute this contrastive learning. That's it, right? We just created 2 more negatives and apply this contrastive learning to increase the probability of the positive pair compared to these negative pairs. That's the video retriever task. And the temporal localization task, which is the given video clip, the entire video and one text query, and then our task is we modeled this as a 3-way classification at frame level. So it's either beginning of that text description, end of that, or other. So for example, if we have these kind of 6 frames and the text is add cabbage leaves and submerge them into broth, then that's happening here. So we have the starting points and the end point in the training data set. And our model is, we trained the model to output the probability that this one would be the beginning one or the end one or the other ones. And we also applied like second order n-grams or bigrams. So these two are combined to become OO. And these two combined to be OB. And these two combined to BE and EO and OO. So instead of just estimating only B and E, we now need to find where the OB and BE is, and that was actually slightly more accurate. So yeah, that's just a minor idea of this paper. So let's see the model architecture of this. So the backbone model was very similar to the VBlbert. So it's basically the cross-model transformer. So starting with one sentence input or text input, and one video input, the sequence of the frames. and it goes to the text encoder, which was BERT, and the video encoder, which was I3D model. And then we have the token embedding sequence. So each of these words is embedded into each of these tokens. And this TCLS is the classification token we usually add in front of the input sequence. Because we have two of them, we just add the T here, text class token. And same thing here. Each of these frame embeddings are encoded from these I3D models. And we add one more special token, V-class VCLS token in front. So now we have sequence of tokens and sequence of frame features in each of these modes. And then we go through the cross-modal transformer, similar to the VBlbert, actually the same as VBlbert. So for each of these queries, it refers to the keys and values in the visual side. And from visual side, for the queries, we refer to the text side keys and values to contextualize. And then goes to text-only transformer and video-only transformer. So entire this setting is repeated for n times. This part exactly same as the VBlbert model, right? We just take the VBlbert model here. And then what we have in the end, each of these text tokens will be transformed or contextualized to all the words in the sentence and also to the frame information in the paired input. And then we pool them using average pooling or max pooling or something to have a single vector representing the text part of this input. And same thing for the visual parts. And then we take the inner product between these two to match it to the VR score, the video retriever score, which means if text is aligned well with this this video, that this will be 1 in the ground truth. And our model needs to figure it out by running this. And for the 0, vice versa. So that is how we train the video retriever model by learning the relationship between the text and the video in the inputs. And for the temporal localization part, the frame level features are given at the end of the video transformer. So each of these are the vector representation of each of these frames, but now they are contextualized to each other within the video, as well as all the text tokens in the paired input. Now, using this text representation and the frame level features, so this will be used kind of query, and we compute the probability that each of these frame is the beginning of what this text is describing within the video, like classifying the B, E, and O, remember? So using this text, given this text, if each of these frame is the beginning of what's happening with this text, and then we also do the same thing for the E, and then we use them to determine where actually that's happening and when it's ending. So that's how we compute the BEO classification for this temporal localization. So, okay, so that's just main architecture. And one additional, actually the main contribution of this paper was applying hierarchical visual encoders. So aligning the text and video segments requires fine-grained spatial temporal understanding at different time scales, because we have very different lengths of videos in our corpus. So the text part is the same. Just text is just one sentence, and it's going to all the different levels. But now video part, we actually have multiple levels. Here we are showing just 2 levels. Input is videos as a clips. In each clips are composed of a sequence of frames. So each of these frames goes through the frame encoder, and they are contextualized by the frame representation within this transformer. Then each of these clips are represented as a single vector. So we have 3 clips here, and they are represented as 3 vectors here. before than that, this frame encoder uses the frame information within each clip to contextualize between them. And then they use some pooling. So this is the representation of the first clip. This is for the second clip. This is for the third clip. And they are combined to a single vector. This one is this one. This one is this one. And then clip level representation is still a sequence of something, sequence of tokens. So we feed this into the clip encoder. Actually, very similar model, almost the same model, just the parameters are different. And this is called video encoder. Then use these clip level representations. We contextualize between the frames within these clip level representations. Then this is the contextualized clip representations. So the same size, but these are the contextualized or the transformed version of these clip level representations. Then if we pool them, then that will be just a single video level representation in the end. So we can actually stack these multiple levels, actually more than 2 if possible, but we have treated only like 10 minutes or 5 minutes of the videos. So we didn't further than that, but actually in theory, we can do even deeper representations. And we didn't try this idea yet, but this text query also can be hierarchical. So in this particular data set, we had only one text query, which is one sentence, single sentence. But if this is a long description of what's happening inside the video, then actually we can split them into multiple levels, and we can build some hierarchical encoders from the paragraphs to sentences, and from sentences to one single sentence, something like that. We didn't try that idea yet. So this is an example of a hammer. So given a query, like he walks out of the door of the shop and walks down the street, and given a video, the task was figuring out where it's happening, when it is happening, and when it is ending. And it shows that the hammer just find almost the correct answer as the ground truth, which is blue here. And the same thing, just an example. Okay, our last model in this lecture is this Hero, hierarchical encoder for video language omni representation pre-training. Yeah, this looks fancy, but actually they are just combination of all the ideas we have already learned. Nothing actually novel, interestingly. So another paper tackling MLVC task, which is very similar to Hammer, but they just aggregated ideas from other models. Let's see one by one. Masked frame modeling, MFM. We heard of this, right? In Videobird. So this is similar to MLM, but they actually propose 2 subcategory of this model. The first one is masked frame feature regression. So this was new, actually. Instead of using the cluster IDs in the Videobird, or instead of using the faster RCNN in the VBlbert or VBlbert, they actually, none of them did this, which is directly regressing to the output of each masked frame embedding. Recall that we mask embedding in the input, and we need to figure it out what it is. That's what we do in the masked language modeling or masked frame modeling. And here, they directly try to regress just by running the direct relationship to those real-valued functions. It was new, but according to their experimental results, this one doesn't work. We don't know really why, but what we know is this kind of masked modeling directly regressing to some vector doesn't really work well, usually. So yeah, this one didn't work out. So their successful modeling was masked frame modeling with NCE, which is introduced already in the CBT. So we already covered this. And the video subtitle matching was, they call it VSM, but that was actually applied in Hammer as well, right? Training a cross-model transformer, which is the VBlbert model, to learn temporal matching between the text subtitle and the visual frames. So Hammer already applied this idea. MLM, masked language modeling, same as original BERT. And frame order modeling, this is also new. So input frames, we have multiple frames in the video sequence, and they just randomly shuffle them. And then the task is reordering them to find out the actual order of those frames, which sounds interesting. And I guess this one will be useful. But interestingly, they had just very minor impact. So my guess is in many videos, actually, the frames may not have the exact order all the time. A lot of actions or a lot of scenes can be actually reversed, and they still make sense, probably because of that. Or the resolution of those frames are too low. I don't know why, but those can be a reason. Anyway, their experimental results say that this one was not as effective as they expected, unfortunately. So they proposed like 5 ideas here, but 3 of them are already known, which was successful. But the other 2 were novel, but they didn't really work. So I don't know what's the point of this paper, but anyway, they combined all of these and did some experiments to figure out what's the most useful, and then this is their final results, which is the video retriever and visual question answering task. So this is their observations for the VR, the VSM and MNC played the most important role. FOM and MFFR are not very helpful, even hurting sometimes, according to this table. So when they add this MFFR, directly regressing to the features, actually the performance dropped for the TVR. But actually for most of them, actually they dropped or just the same. So this one was completely failed. And for this FOM, this one was not useful for the retriever task from 2 to 3, but that was actually useful for the VQA. So it depends on the actual task they apply. So that was an interesting observation. And at least for some tasks or the data sets, they were the state of the art at that time, which is last year. So I just added this paper. So yeah, this is the end of lecture 17. I originally wanted to finish lecture 18 by today, but we are slightly left behind, but we have just 3 more minutes left. So I don't know. We can just stop here today. And if you have any questions, just ask now.